Electric potential and capacitance. Effect of dielectric on various parameters. Case 1. When power supply remains connected and a dielectric is inserted. In that case, charge Q becomes K times Q0. Q0 is original charge, K is dielectric constant. Now, potential V remains V0, that is, it remains original. Then electric field E remains E0, no change. Capacitance becomes K times C0, where K is dielectric constant and C0 is original capacitance. And potential energy U becomes K times U0. Now, case 2, when power supply is disconnected and a dielectric is inserted. In that case, Q remains Q0, V becomes V0 divided by K, E becomes E0 divided by K, capacitance becomes K times original capacitance, and potential energy decreases by a factor of 1 upon K, that is U0 upon K. Next point. Force on each plate of a parallel capacitor. Now, if we try to increase the separation between these two plates by a distance dx, then work will be done against the force of repulsion. So this work is dw, which is F dx. Now, increase in volume of capacitor will be equal to area times distance moved, E dx. Now, we know that energy density is given by energy divided by volume. So from here, we can get energy equal to energy density U times volume. Now we put the values. So, and also we know that energy is equal to work done. Now, so we write work done F dx equal to energy density is given by 1 by 2 epsilon naught E square, and volume is A dx. From here, dx will cancel out and we will get F equal to 1 by 2 epsilon naught E square times A. Now, what we can do? One can write E equal to Q upon epsilon naught A. So here we make such changes, 1 by 2 epsilon naught. We retain one E and replace another E by Q upon epsilon naught A. So from here, epsilon naught and A will cancel out and we will get force equal to 1 by 2 Q times E, where Q is the charge and E is the electric field. Now, let's consider next question. Question says 3 points A, B, C lie in uniform field E equal to 5 into 10 power 3 Newton per Coulomb as shown. Find the potential difference between A and C. Clearly, potential at B and potential at C will be equal. So this angle is 90 degrees. So we can apply Pythagoras theorem to get AB as 4. Now, potential difference between A and C is same as potential difference between A and B. So we know that E equal to minus dB upon dr, and here dr will be this distance AB, and we have to find out potential difference. So we can say dV equals minus E times, in place of dr we can write dx as this distance. So we put the values, dV times E is given as 5 into 10 to the power 3, and dx is distance 4 meter. So if it is 4 meters, so just we multiply and we will get minus 20 into 10 to the power 3 volt. Now, this question can be given in terms of centimeter also. In that case, this will be 3 centimeter, this will be 5 centimeter, then this will be 4 centimeter, and then we have to convert this 4 centimeter into meter. In that case, answer will be 5 into 10 to the power 3 with a negative sign times 4 divided by 100 volt, and that can be done. Now, let's see next question. N drops of mercury of equal radii and possessing equal charges combine to form a big drop. Compare the charge, capacitance, and potential of bigger drop with corresponding quantities of individual drops. So let's consider the smaller drop. For smaller drop, its capacitance is 4 pi epsilon naught small r, and its potential V will be equal to Q divided by 4 pi epsilon naught small r, where small q is charge on each small drops. Now, if bigger drop has radius r, so we can say that 4 by 3 pi capital R cube will be capital N times 4 by 3 pi small r cube. Here, n small drops combine to form a bigger drop, so volume will remain same. Now, let's simplify. So we get r cube equals n times small r cube, from where we can get r equal to n power 1/3 times small r. Now, charge on bigger drop will be capital N times small q, which is equal to capital Q. So charge on bigger drop is taken as capital Q, and the charge on smaller drop is taken as small q. Radius of smaller drop is smaller, whereas radius of bigger drop is capital R. Now, capacitance of bigger drop, so it will be C dash equal to 4 pi epsilon naught capital R. Now, if we find the ratio C dash to C, so what do we get? We will get from here C equal to 4 pi epsilon naught r, which is capacitance of smaller drop, and C dash is capacitance of bigger drop. So the ratio will be capital R to small r. But here, if we try to get capital R to small r, we will get n power 1/3. So here, answer will be n power But now let's compare the potentials. So let's V dash is the potential of bigger drop and V is potential of smaller drop. So V dash from this formula, it will be Q divided by 4 pi epsilon naught capital R times Q divided by 4 pi epsilon naught small r. So here we get capital Q upon small q times small r divided by capital R. Now we put the values. Capital Q upon small q will be equal to capital N times small r to capital R. From here will give n power minus 1 by 3, from where we can get V dash upon V equals n power 2 by 3, which is our answer. Now let's go to next question. What is equivalent capacitance between A and B? So here, this is case of balanced bridge. So when bridge is balanced, in that case, this capacitance will be removed, and equivalent circuit will look like this. C, 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 C. Here, this capacitance was connected like this. This one is removed. So let's not write it. Now, this is C, 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 C. These two are in series. So equivalently, we can write this will become C by 2. This will also become C by 2. Now, these two capacitances are in parallel. So equivalent capacitance will be C by 2 plus C by 2, that is C. So this is our answer. Now let's go to next question. What is equivalent capacitance between A and B in given network? Here, this is infinite network. So this is 1 microfarad, this is 2 microfarad, then 1 microfarad, then 2 microfarad, this is 2 microfarad, then this is 1 microfarad, and so on. So we assume equivalent capacitance as C. So we can write it like this is point A, and then this one we are going to write here. So this is 1, and then this 2 is written, and then remove entire thing and assume it equal to this portion is removed, and we assume that this is equal to C, and the whole resultant is also C. So this is 2, this is 1 in terms of microfarad, this is also microfarad, and this is C. And we have assumed that equivalent capacitance is also equal to C, because from an infinite network, if some portion is retained, still total sum will remain same. So here we have removed this portion, this is infinite, and only this portion is retained, and we have assumed that the right portion has capacitance C, and when we add this portion that we have retained to the equivalent resistance, so still we get C. This is just assumption, and on the basis of this assumption we can solve this question. So let's see, these two capacitances are in series and this is in parallel, so we can write it as 1 plus these two are in series, so it will become 2C divided by 2 plus C equal to, we have assumed it as C. So it will become 2 plus C plus 2C equal to 2C plus C square, from where 2C will cancel out, and we will get C square minus C minus 2 equal to 0. If we factorize it, so we can write it C square minus 2C plus C minus 2 equal to 0. So C minus 2 and C plus 1 equal to 0. So C will be 2 microfarad, and C cannot be equal to minus 1 microfarad. So our answer is 2 microfarad. Now let's go to next question. Determine the potential difference between VA and VB points A and B that are shown here. Now, what is the condition for it to be equal to 0? So let's evaluate what is the value of VA minus VB, and after that we will put it equal to 0 to get the condition. So now this is potential difference source. So suppose charge Q1 flows in this branch and Q2 flows in this branch. In that case, we can say that V equal to, for this capacitance we get the voltage, and for this capacitance we get the voltage, and sum of these two voltage must be equal to V. So Q equal to CV gives V equal to Q upon C. So we can say Q1 upon C1 plus Q1, same charge will flow in this also. So Q1 upon C2, from where we can write Q1 1 upon C1 plus 1 upon C2, or Q1 times C1 plus C2 divided by C1 C2, which is B. Our concern is to get Q1. So let's write it. Q1 equal to V times C1 C2 divided by C1 plus C2. Now let's see this branch. Charge Q2 flows through this branch. So again, we can say potential difference across this plate plus potential difference across this plate will be equal to total voltage applied. So we can say that V must be equal to Q2 divided by C3 plus Q2 divided by C4, which is equal to Q2 common 1 upon C3 plus 1 upon C4, which is further equal to Q2 times C3 plus C4 divided by C3 C4. Our purpose is to get Q2, so Q2 will be equal to V times C3 C4 divided by C3 plus C4. So we have got the values of Q1 and Q2. Now we have to find out VA minus VB. So VA minus VB. VA minus VB can be written as VQ, potential difference at this point. So we can write VQ minus VB minus VQ minus VA. Now, if we observe in the circuit, so VQ minus VB will be potential difference across C4, and VQ minus VA will be potential difference across this capacitance, that is C2. So we write these values. So we get Q2 divided by C4 minus Q1 divided by C2. We can put the values of Q1 and Q2. So we get VA minus VB, and we have got Q1 as V times C3 C4. So from here, C3 V times C3 C4 divided by C3 plus C4, and here C4. So once C4 will cancel out. Similarly, we have got the value of Q1 as V times C1 C2 divided by C2 times C1 plus C2. Now C2 will cancel out from here, C4 will cancel out from here. So we will get V times C3 divided by C3 plus C4 minus V times C1 divided by C1 plus C2. So this is VA minus VB. Now we can take common V and then we take LCM. So C3 times C1 plus C2 minus C1 times C3 plus C4 whole divided by C1 plus C2 times C3 plus C4. Now, if we open the bracket, C1, C3 will cancel out. So we will get V times C2, C3 minus C1, C4 divided by C1 plus C3, sorry, C1 plus C2 times C3 plus C4. So this is potential difference between A and B, that is VA minus VB. Now, the next part of the question says, what is the condition for this potential difference to be zero? If we equate this potential to be zero, then from numerator C2 minus C3, C2 minus C2, C3 minus C1, C4 will be zero because other terms can't be zero. So in that case, we will get C2, C3 equal to C1, C4, or C3 by C4 will be equal to C1 upon C2. So this is a required condition to make the potential difference to be zero between points A and B. Thank you for watching.